On va parler de machine learning, un sujet passionnant dont on entend très souvent parler. Et pour cela, on n'a pas fait les choses à moitié. On a fait venir une personne qui nous vient tout droit des États-Unis, de Boston, Monsieur Victor Oancea, qui arrive de suite. Et je vous prie de vraiment faire un tonnerre d'applaudissements parce qu'il est venu ce matin très tôt pour l'occasion.
Merci beaucoup. Tout d'abord, je suis très heureux d'être ici cet après-midi pour essayer de commencer une conversation sur machine learning and multiphysics simulations. And with that, I'll stop in French because otherwise it would be a disaster. So I will switch to English forward. Okay, so machine learning for design exploration. I would like to take you to a journey of what we have been doing the past, 9 months or so in this area with some successes that we have attained, and to tell you where we are and where we're going in the next year or so. So this is a picture. What can AI do for you? And Delphine mentioned ChatGPT this morning. Can you combine an image from the left with the style of the cartoon on the left with the picture in the middle and to create something new? And it's incredible to think that today this is quite achievable, very easy. Multiple software packages can do that. Obviously, not too relevant for what we do here at SIMULIA and NDS, but can one rapidly combine previous knowledge into new designs, let's say, as a little bit of a parallel in here. Okay, a little bit of a grand statement, perhaps too much. Let's come a little bit down to earth from that. You've seen from us models like this that have to do with multi-physics-based simulations for heart models. Here's a little bit of a thermomechanical, electrical, fluid type simulation, very sophisticated. We spent years making it functional. It can be used for simulations of pre-surgery type operations to clamp the valve in a virtual heart like this, but it's way too expensive. Obviously, as it is today, it cannot be put in the hands of clinicians. So the idea is that can we make this a lot faster, such that if you put it in the hands of non-experts, this becomes something that can become a predictive tool pre-operatory, let's say, for a surgeon. So the answer we have for this, we call it high-fidelity 3D surrogate models, just to give it a name. And I'm going to skip this slide because the time is short, but the idea is that surrogate modeling. Surrogate modeling means a lot of things, depending on who you talk to and what forum you talk to. And we thought it would be good to give a little bit of a definition of what's going on. So on the right side, reduced order models. On the left side, machine learning models. So on the right side, if you can read the screen, pretty big, yeah, the font. So the idea is that methods in green, we had them for a while now, for decades. Crank-Badminton stands for substructures or super elements or flex bodies, pick your favorite name. We had them for decades now, they're quite reliable. I'm not gonna describe what we do in the methods in orange. We are working on them. Think of them as non-linear substructures in a way. We are active, we are making progress, and we're not quite there yet in terms of talking about that for industrial applications, but perhaps we'll talk about them next year when we come back to this. On the left side, machine learning models, and the vocabulary has changed the past 4 or 5 years. Today in machine learning models that are included things such as listed there in green, and I'm not going to read them, that most of you perhaps have already exercised for many years. But the idea is that if you look at the 2x2 matrix here at the bottom, stationary, transient, scalar KPIs, 3D field KPIs. If you look at the methods in green, typically they're used for applications in the upper left corner of the 2x2 matrix. You typically look at things such as max stress, minimum mass, one number, max temperature, let's say, from whatever sophisticated suite of analysis you are running in order to be able to do some conclusions based on that max number, let's say. Neural networks tend to be very useful, and hopefully we think a whole lot better for the other 3 cells in this matrix. First of all, if you're looking at transient applications and you're trying to predict the entire transient history of that curve, of whatever physics you're trying to model. Transient scalar KPIs. But very importantly, it's for the bottom row here, if you're trying to predict 3D field KPIs, by far we think deep learning or neural networks type technology are the far superior compared to the rest. So before I dive into some examples to hopefully convince you that we have something that's promising, let's see how we do things here. So machine learning for 3D design exploration. We divide it in 3 phases, and if you have worked at all as far as preparing surrogate models, you would not be surprised at what you see on this slide here. So first of all, parameterized models, we start from parameterized models. And what do we mean by parameterized models? First of all, geometry, dimensions, thicknesses, etc., composite layups, you name it, whatever can be parameterized from a CAD perspective. But also loads and also materials. So loads can be specified of any kind over whatever ranges. Materials can be swapped in and out. In a nutshell, that's what we mean by parameterized: geometry, loads, and materials. Then we run a DOE, a design of experiment, over that parameter space, whatever it is. And perhaps it's going to get a lot clearer when we go through some examples. And then we have a phase that we take this data from these many simulations and we prepare the data for machine learning exercises. How to train a machine learning model on the right side of the screen right now. Out of all 3 phases that you see here on the slide, this is definitely the most expensive, meaning running a bunch of simulations, and you'll see how many in a minute, takes anywhere between hours and days. And as far as an overall computational process, this is definitely the most expensive phase of the entire process. Okay, on the right side, on the top side, you see basically train a machine learning model. So you take the data from the left side, from the top side of the slide, and then feed it into a process that will train a machine learning model, and what comes out of it is a executable, just like any other executable, that basically will take inputs and will produce outputs. And the inputs are shown here at the bottom by the dials that you see here when you're trying to make a prediction. So you train the model, and now you're trying to get a prediction of what's happening from that machine learning model when we change the parameters that can be either geometry, loads, or materials. So you see here some 4 geometric parameters that are input into the machine learning model, and out comes a contour plot like you see here on the right. So altogether, run a DOE over a parameterized space, train a machine learning model, and then use that machine learning model executable to make predictions for designs that you have not run simulations for. So that is kind of the overall process, and the idea is that we try to convince ourselves that it's actually working. So are these predictions accurate? Are they for transient KPIs and for 3D field outputs, whether you're trying to predict one frame of data, like the stress contour plot at the end of a multiphysics simulations, let's say, or a full animation in a 3D sense of deformations or stresses or whatever it would be necessary for you to be able to make decisions. How much offline training does it take? And I'll give examples and tell you how much in a second. Do predictions improve with training? Are the predictions reliable? Are the models accurate such that you can make engineering decisions in a consistent sense with high degree of confidence? So to demonstrate to ourselves and hopefully to you too, we looked at the 8 highly nonlinear multiphysics applications. 6 of them are abacus-centered, but not just abacus, and 2 of them are fluids, and we're working on electromagnetics and the multi-body dynamics applications as we speak. So M1 through M6, you see at the top, first is a tube crush, a landing gear, a heart valve from the heart model that I showed before, a welding application, a bottle, and a battery pack, M1 through M6. In all cases, we have parameters. On the left side, for M1, we have 4 geometric parameters, 4 dimensions, 3 dimensions and a thickness, I'm sorry. And on the second one, we left the geometry the same, but we're varying the loads. Can we do design exploration via machine learning in that case? In the M3 case, we combine all things together, meaning we swap in materials, we have different geometry parameters, we have different loads histories in there. And back models, model 4 looks at process parameters for a welding process, like you see listed there, and M5 and M6, again, back to geometry type parameters. And the idea is that, can we predict the KPIs that you see listed at the bottom? So let's say on the left, KPIs for the scalar RF reaction force, if you're an abacus person, and 3D deformation. So you see in the little inset at the bottom of the screen on the left side, an XY plot that shows the reaction force as a function of time. And when we show curves like that in all plots that will follow, in red will be, in this case, an abacus reference solution, and in blue, a blind prediction from the trained machine learning model shown on top. So, and I'll show comparisons in detail as we go along. At the bottom left, again, you see two 3D contour plots. When you show things like this, on the right side, we show an abacus reference solution again. And on the left side, we show a machine learning prediction model in a blind prediction type sense. So again, everything that I'll show results for will be in a blind testing prediction type environment. We also did two fluids application on airfoil. The idea is that for 3 geometric parameters, can predict all the things that are listed there on the bottom left, or a little bit more complex from a full car application flow around a car, as you see here in model 8. Can we predict the contour plots of pressures and fluid velocities around the car through a machine learning type technique? And I'll pause on that example towards the end. So perhaps what I'll do next, I'll go in more detail about the first example, just to give you a little bit of a sense of what we do. So tube crush, model number 1. So if you're working in automotive, you may be familiar with this test. We're looking at a rectangular cross-section type tube here. The idea is that there is a big mass on the left side of the tube. It's fixed at the right end with the gray wall over there. The idea is that when that big mass hits at 35 miles per hour, as listed here, it's going to produce a deformation mode that's energy absorbing. It's called an accordion type mode. And again, automotive companies work quite a bit to try to optimize that mode such that the energy absorbed is optimized. You see here in WHLT the 4 geometric parameters that we have, and you see the ranges there listed on the second line under the bullet. If you picture the ranges, they are fairly large. They're not quite small as far as how big they are for a design space. One, elastoplastic rate-dependent plasticity model. It's a real automotive material model. It's not a made-up, simplified thing. So one more time, elastoplasticity rate-dependent. We run 50 milliseconds of abacus explicit type analysis. The idea is that, can we predict the reaction force on the gray wall? Can we predict the deformation pattern? So the way we did it is we run a DOE with 16 simulations, one more time, 16 simulations. Abacus runs, we collect the data, we train a machine learning model, and then we perform 64 blind testings to verify that our model is correct. Again, over the same parameter space that is listed at the top, but again, very different points in the design as far as the 4 parameters are concerned. So when you do that, again, you get something like this. So on the right side, again, it's a abacus reference solution. On the left side is the machine learning blind prediction. And you see on the left side, prediction number 10 out of 64 as listed there. So out of the 64, we're showing just one because of economy of time. And we are predicting all the 30 frames that came from that simulation. So 30 frames of data predicted. Do we claim that they are identical? No, they're not identical. Can you make decisions, though, design decisions based on the information on the left, if that helps you when compared to the information on the right? We think so. But again, that's something for you to decide if you decide to work with us. So just to give an example here, in execution time here, abacus, this is a very small abacus model. It takes about 6 minutes to run on one CPU. Machine learning takes about 3.6 seconds to execute the 30 frames of data. In general, for machine learning predictive model, it takes more to plot than to compute. So that's the first example, and hopefully that paints a picture to you. How about reaction force on the wall? So again, we trained from the 16 training simulations that I mentioned before. And then we did the 64 blind predictions again. We ranked all the results from these 64 in a norm error sense, an RMSE type sense. So we did that separately, and now we're plotting the 4 best at the top and the 4 worst in a second at the bottom. So the 4 best look pretty good. Can you make a decision based on blue, which is the machine learning prediction, versus red, which is the abacus reference solution? Again, a blind testing environment. We think so. If you look at the worst out of the 64, though, the results are not so great anymore. And the idea is that, yeah, it's way faster. It takes 80 milliseconds to produce a graph like this, like you see here, but it's a little bit inaccurate. So the idea is that now, if you see there training from 64 training simulations, now we revert the two sets, 64 for training and 16 for blind predictions. And we're showing the 15 worst on the slide here. We're showing 15 because otherwise they would not fit on the slide. And the one that the worst is the one on the middle row at the right extreme, meaning the results got a whole lot better with more training. And just to give you a sense here, the training period here took about, in this particular case, when you use 64 training, it took about an hour and a half on a P100 card, if you're familiar with the NVIDIA cards. An hour and a half is definitely, you know, it's pretty fast for this model, but this is a small model. We'll get into more serious example in a second. So that's example number one. Perhaps it proves a little bit, that shows a little bit that we think these methods have a chance for highly nonlinear applications for both 3D field predictions and also for XY plus, like reaction forces, whatever, if you're an Abacus person, whatever it's a history output in Abacus. Here's a second example with landing gear. We kept the geometry just the same. The idea is that can we predict over those ranges for fx, fy, fz, and if you look at the numbers, it's quite a wide range for mimicking landing loads. Can you predict the stresses in the green part over there? And this is an elastoplastic type material. It's a large deformation type analysis. The idea is that how accurate the results are. Same idea, we train from 16, we predict for 64. And if you look at the best prediction at the top, training from 16 looks very good. It's the same plot that Delphine has shown this morning. However, if you look at the bottom plot, results are not so cool anymore, meaning the differences between the machine learning prediction on the left versus the Abacus reference solution on the right, they're quite significant. And same idea, now if you revert, we train from 64, and the top right, the best results remain pretty much the same. The worst result gets a whole lot better compared to the left side of the slide. Are they identical? No. You still see some differences in red on the cylindrical part at the top. But again, can you make decision now based on this stress contour plot from machine learning versus the one computed by Abacus reference? We think so. And again, it takes about 5 milliseconds to compute a frame of data like this. It takes longer to plot when compared to compute. Okay, so perhaps this is the most nonlinear example that we have done in multiphysics, if you will. Example number 3. The idea is that it's a co-simulation exercise between Abacus and Daimola. If you're familiar with what Daimola is, it's another product that we have from CATIA Systems in the Dassault System family here. The idea is that this is a mitral valve between the left and right atrium in the heart. It's a model, of course. We're not debating here if you believe the 3D results, although we have spent 10, 15 years trying to make these results as realistically as possible. The idea is that how can machine learning speed up these computations quite a bit post-training? So there's 23 parameters in this setup here. Just to look at the geometry a little bit, and I'm going to talk only about the first parameter, is if you look at the center bottom figure, there is looks like almost like a circle from a top view. That diameter varies anywhere between 24.1 millimeters to 45.2 millimeters. So from children to adults, it's a quite wide space as far as the parameterized geometry is concerned. And we apply pressures on the top and the bottom of the leaflets of the valve. They close, they open, like in a systolic, diastolic type cycle. As far as the heart beating is concerned, we show there in the XY plot 2 beating cycles. If you look at now, so again, we have 223 parameters, so a whole lot more than before. Therefore, we need to train from more simulations. So yeah, this is 540 simulations now we train for. So quite a handful. Just to get a look at the bottom right here, it says Abacus reference solution for each of this simulation takes about 54 core hours or 2.7 hours on 20 cores. It's still a small Abacus model, but it's pretty intense from a numerical perspective. To produce a frame of data with machine learning algorithms, train algorithms like this, like you see here, it takes about 0.24 seconds. So again, it takes a whole lot more to plot than to actually compute. In each panel, we show on the right side a abacus reference solution, and on the left side again blind prediction by machine learning. You make up your own mind as far as how good it is. We think it's pretty good. Are they identical? No, they're not identical, but can you make decisions, and if you believe the results in full 3D from abacus, can you use the machine learning now, train machine learning predictions to be able to make decisions? We think so. The curves here represent the area of the opening that was, I didn't talk about it, so basically the fact the valve is not closing. Again, red is an abacus reference solution, blue is a machine learning prediction. Again, not identical, but pretty close for a very highly transient application and very nonlinear materials, hyperelastic, viscoelastic material, a lot of connector modeling in the tissue there, healthy tissue, diseased tissue, and so on. Let's keep this example. Say some bottles example here. Here's some sample geometries that you just saw in terms of, I'm going to flip them back and forth. A pretty wide design space. We show some sample geometries here to get a sense of what design space is. We apply a load at the top, elastoplastic material. You get the idea. If you want to plot reaction forces here, you can barely tell them one from the other. Machine learning versus abacus, meaning even the ones that are labeled buckling, if the curve goes from downwards to upwards, there is a buckling behavior happening, meaning an instability is being captured as well. Last example that I want to show from the abacus side here, a battery pack, 120 parts in this model. So far I've shown one part examples. Now this is an actual assembly. Side impact of a battery pack. If you had to design what's called the rocker arm, the one that zoomed in at the bottom center, through a range of thicknesses like you see listed there, how can this happen? So again, if we train from 60 simulations, we show the best results at the top, blue versus red, quite close to each other. The worst one, not so good at the bottom, but again, same idea. If you train from 128 simulations, the worst results before become much better with more training. And again, it takes almost no time to predict that kind of results. Same idea for the 3D deformations. If you're looking for such deformations, you can focus only on the 6 parts that you are actually after to redesign, let's say, as we show at the top. We produce 50 frames of data from the machine learning model here, compared again on the right side with an abacus reference solution. At the bottom for 22 parts, things are quite accurate, without, again, with not claiming that the results are identical. And I'll show this example for CFD applications. We heard about LBM for turbo machinery this morning. This is a LBM modeling of airflow around the car for drag coefficients and so on. You see playing at the bottom here the morphing parameters that are used to span the design space on the bottom left in terms of car dimensions and shapes. In addition to that, the deflectors that you see a little bit in the center panel, they are on or off. We run a 24 testing set to train a machine learning model. And the idea is that how do we do as far as predictions are concerned in this case. So if you look at pressures, CFD in this case, Lattice-Boltzmann with power flow versus machine learning on the left. Even if you look in detail, mirrors and tires and whatnot, things match quite well. Just to go back a little bit, you see on the right side, it takes thousands of core hours to execute a Lattice-Boltzmann model like this. Again, it takes about 0.2 seconds to run a model, to come up with a prediction, to compute a prediction via machine learning. I want to point out the amount of data that's being trained with, in this case, in total, you see that number 1.53 billion floating point numbers that are being used for the training, so a massive data set. There are about 7 million points on the surface of the car where we do predict pressures in this case. All right, so a quick look into the future. We are producing apps to leverage all this technology right now. They would probably be, no, probably they will be available in the first half of next year. They will be part of the design exploration family of 3DX apps that we have already. It's going to be called Performance Guide. We're going to use this technology underneath to be able to train machine learning models. It's going to offer an environment to collect, to run the DOE, collect the data, train the machine learning model, have your own expectations in there, bring your own IP if you don't like what we do in there, and basically in the end, at the inference or the prediction state, as it's called, you're going to get views like this, that you get dials at the top left. You're going to get views for the key KPIs that you chose, in this case, a stress, a plastic strain, etc., to show here in the view, and at the bottom, a reaction force plot as an example of what things you could look. First half of next year. Just to give you a sense of how this is going to look like, so this is a video that is not sped up. This is for real. It's not any quick speed upping of the screen recording. So what's happening here, look, apply the parameters. If you see, click. It's going to play in a second again, I think. Probably not. Let me see again. So choose a parameter, you change it to a number, apply. What's happening next? The curve geometry, gray, changes to a straight geometry. This was geometry generation. All the other phases listed on the right are executing with a 0.2 millisecond, 20 milliseconds only for the computation. So all the other phases, you see here a 12-second video. This is, again, what you should kind of expect for sometime next year. So that's kind of a quick quick view into the future. We're also working on other activities in terms of improving on the technology, meaning the topic of continuous learning. You run simulations over the years. Can you leverage all simulations into new workflows? And we're learning how to do that today. If you add a new parameter, the O parameter in here, how that learning that you've done in the past without the middle wall can be leveraged such that something with the O parameter included is much faster in the ability of training a new machine learning model. And again, we show here bottles, but applies to many products. If we have a model in 2023, this topic of geometry encoding or auto-encoding, maybe some of you have heard of it. How can it be used that you come up with a bunch of geometry that are not parameterized, are brought into the mix here to come up with a second generation machine learning model in the middle. And for 2025, let's say as a metaphor, the idea is that you might not need to run a abacus simulation, the one in white font at the beginning in the design exploration stages, but you only do it for certification at the end to speed up the design process that you have. And if it works for bottles, it might work for these things too. We don't know yet. That's active research, as you see here in the top right. We are ready to engage now, though. These apps are coming next year. So 2 more slides. This is one video that's playing what we have right now. So this is based on process templates on the 3DX experience. We have a similar process based on iSight and Python scripts and Abacus, but again, this would be definitely the more interactive way to do things. We offer already an environment to train, to run the DOE, to train, to explore the training, get the dials like you see playing here for predictions, to look at 3D plots like you're going to see in a second playing on the right side. This is definitely sped up compared to what I've shown before, so this is not the speed that you're going to get, but today, but the previous video was. And last slide here. We would like to engage with you now, like I mentioned. We already have made presentations like this to customers in many geographies and many industries. We would certainly like to hear more from France, a little bit more. The idea is that we did present this here. If you kind of think that this might be useful to what you do, we would be very happy to make another presentation to you, and you get to stop us and ask questions and probe us and etc. to find out more things about what we do and what we don't do. Then you get to think about in number 3 here. Can you formulate a problem that you think that this might be useful for your enterprise? And if you can spend in a slide, no more than 1 slide. Think about it, then we have another discussion, we iterate, and perhaps we have a project, and we already have a number of projects going on like that in various industries across the globe. And then we deliver to you how to train, first of all, the trained machine learning model, and then that we teach you how to train models and so on. And in number 7 here, whatever, if you like what you see from us, integrated with what we have, the idea is that we get to incorporate your feedback right now in the apps that we develop. So when they hit the market sometime next year, your feedback is already incorporated. And with this, merci pour votre attention. Et j'espère que ça c'était intéressant pour initier une discussion sur ce topic. Merci.